Welcome to edition 77 of the Food Safety Fridays webinar program. It's great to be back after a couple of weeks away. I've missed it. I've missed you all. I hope you've missed me too. Well, do you use compressed air in your business? I wager if you make things, food, what we're talking about, you do use compressed air. So do you test it? What do you test it for? When do you test it? Why do you test it? How do you test it? Who tests it for you? Some of those questions will be answered today by our guest presenter, Ruby Ochoa from Trace Analytics, LLC. We'll be going over to Ruby shortly, but just to say, today's webinar and the Food Safety Fridays webinar program is sponsored by none other than Trace Analytics, Metal of Toledo, Safe Food 360 and AIB International. These kind organizations support us and help us to bring these regular webinars, free education, and you get a free certificate of attendance. Just to draw your attention to the sidebar, I know a lot of you are typing in there. Throughout, you can type your comments, say hello to each other, get to know each other, post your questions, and we'll pick through those at the end. And also, we'll be setting some polls during the webinar, a couple of polls that we'd like you to vote in. So please do engage with the webinar and help it to make it even better. Okay, so at this point, I'd like to introduce you to Ruby Ochoa, President and owner of Trace Analytics, LLC. Welcome. How are you doing, Ruby?
I'm doing fine, thank you, Simon.
Yeah, you look fantastic.
You're too kind.
As I said before, that's the best backdrop we've had on here. So after 77 webinars, you're onto a winner already.
Well, thanks. We appreciate that. Marketing team did a great job on this presentation. They
did, actually. I've seen the PowerPoint, and it's very, very professional. It puts me to shame. Can you just let the ladies and gents know where you're based, where you're calling in from today?
Absolutely. We're located in Austin, Texas, and a little sort of on the edge of the hill country. So we have some beautiful views, although the traffic is awful in Austin, Texas.
Is it? All right, well, we're free of that for an hour at least anyway. So if you want to get your slides ready, Ruby, I'll tell the audience about next week's webinar.
Great.
Okay, ladies and gents, next week we have David Rosenblatt, and he's going to be discussing food safety and employee safety, a behavioral approach to create synergy by integrating two agendas. You can register in the sidebar directly or respond to the emails, and that's going to be great because David Rosenblatt is fantastic. I'm sure many of you know. Right, I'll be back for some polls and the Q&A later, but for now, I'll hand you over to Ruby. Okay, Ruby.
Okay. Well, we all know that compressed air is a critical utility that is widely used throughout the food industry. Many of the GFSI schemes like SQF, BRC, and many others require compressed air quality monitoring. FDA's Food Safety Modernization Act requires covered manufacturing facilities to establish and implement a food safety system that includes an analysis of hazards and risk-based preventive controls. Knowing which contaminants may be in compressed air is key to avoiding product contamination. Your task is to assess the activities and operations that can harm a product, the extent to which a product can be harmed, and how likely it is that product harm will occur. Assessing product contamination is a multi-step process in which you must identify the important risks, prioritize them for management, and take reasonable steps to remove or reduce the chance of harm to the product, and in particular, serious harm to the consumer. In this presentation, I'll be discussing contaminants in compressed air and why they may be harmful to your product, how to use the blank checklist we provided in our download section to assess the hazards associated with compressed air, and air quality specifications and guidelines. As a first step, let's identify the potential hazards in compressed air, the contaminants. A number of components of ambient air become contaminants once they enter the compressed air stream. When a compressed air component has a harmful effect on the product, it's then considered a compressed air contaminant. So what are the contaminants in compressed air? Both the Compressed Air and Gas Institute and ISO 8573 specify compressed air contaminants. CAGI cites 10 contaminants that typically need to be removed or reduced from low-pressure compressed air used for manufacturing. These 10 contaminants fall into 4 general categories. Particles, which include pipe scale, wear particles from compressor operation, and atmospheric dirt. Water, in liquid, vapor, and aerosol form. Oil, also in liquid, vapor, and aerosol forms, and microorganisms, which are also described as non-viable particles. The international standard ISO 8573 is a compressed air quality specification that addresses these very same specific contaminants by providing a range of purity classes for particles, water, and oil. It does not include purity classes for microorganisms or gases. Gases may also be considered a contaminant if your product can be harmed by gases like carbon monoxide, carbon dioxide, sulfur dioxide, nitric oxide, nitrogen dioxide, and hydrocarbons with 5 or less carbons in the chain. This is unlikely because they're present in the air that we breathe every day. So the primary sources of contamination in a compressed air supply include the intake air quality and the compressor itself. Other significant sources include storage receivers, distribution piping, and items that are connected after the point of use, filtration, such as valves, gauges, flexible tubing, and fittings. So let's discuss some of these hazards. Air pollution is not only a public health and environmental problem, it also contributes contamination in the form of millions of particles per cubic meter. These particles consist of acids like nitrates and sulfates, organic chemicals, metals, and soil or dust particles. Coarse particles are between 2.5 microns and 10 microns in diameter. The finer particles with a diameter of 2.5 microns or smaller are not removed by the intake filter and pass right into the compressed air system. Particles can be categorized into 2 different types, viable and non-viable. Viable particles are microorganisms, such as bacteria and viruses. Non-viable particles consist of things like rust, pipe scale, and dust. I'll cover viable particles a little bit later in the section. The compressor can contribute wear particles from its operation. Wear particles can be metallic or polymeric. Particles can also be generated from a compressed air system that utilizes a refrigerated dryer with iron distribution piping or receivers. The combination of high water and iron will form rust and pipe scale. Using iron piping is quite common in food manufacturing facilities. Aluminum piping is another source, creating fine dust in the form of aluminum oxide. Same thing with copper piping and it creating copper oxide. Particles can also be generated from a desiccant dryer. That's why a particulate filter should always be installed after a desiccant dryer. Unions and valving of the piping system are critical in that material used for seals can shed particles and have a tremendous negative impact on air quality. Another source for failure for particle requirements is the use of some flexible tubing in the process line or the sampling procedure. Careful consideration should be given to the type of polymer tubing used because if it's not rated for low particle shedding, many types of polymers like rubber will continuously or sporadically shed significant particles. Some can also allow ambient water vapor to diffuse into the tubing. This can adversely affect the quality of dry air by raising the vapor levels. There are suitable types of tubing that are designed to have little to no particle shedding or permeability issues. They may not be easy to find if you don't know what to look for. Manufacturers label these types of tubing in a variety of ways: pure air, sterile air, high purity air. Also, you can look for their recommended applications as a key, like air sampling, high purity, food grade, and then the properties that are required to keep those particles out include cleanliness, chemical and UV light resistance, resistant to high ambient temperatures with low moisture absorption, and low particle shedding. You should get your vendor to provide you with the specifications for the type of tubing you're using. And if you are using tubing after the point of use filters, you should check with your vendor that it has the correct properties to prevent contamination of your product. Occasionally, we have clients that can't figure out the source of particulate contamination. After troubleshooting and repeated sampling to eliminate the obvious sources, we recommend that we can send samples of the samples with particles to a different company to identify the particles by composition. So what you see on the screen is some of the information that we can get about specific particles. In this case, they determined that the black particles were most likely bits of charcoal from the system's filtration. And the chart on the right identifies each chemical compound detected. One of the clients, we had 2 clients that had this issue like within the last month. And one of the clients determined that damage had occurred to the filter inside the filter housing. When they opened up the filter housing, there was charcoal all over it. For some reason, they hadn't looked in there during all our troubleshooting efforts. The other, it just happened last week, so we're still waiting to see what they discovered. Another client also had this type of analysis done, and they determined that it was abrasing brass from the piping. So interesting information if we have to go down that road. It is available. So let's go on to the other potential contaminant, which is water. Speaking of water, I think I need to take a sip. Much better. Atmospheric air typically contains 1,000 to 50,000 parts per million of water, depending on where you live. If left untreated, compressed air with high levels of water is unacceptable for critical applications. Excess water will cause corrosion in iron piping and storage receivers, like I mentioned before, and that type of particulate contamination can damage equipment used in your production lines and contaminate the final product. Drops and dead ends in the distribution piping can trap water and create an environment for microbial growth. Water can wreak havoc on the piping system and cause particulate damage, as I mentioned before, but in a water-saturated system, aerosols can be generated from water collected on piping walls and mist your final product. Now, the third hazard or contaminant is oil. Atmospheric air typically contains between 0.05 milligrams per cubic meter to 0.5 milligrams of oil vapor. Common sources are vehicle or motor exhaust and industrial processes. There are so many different words to describe oil, it can be confusing. Common terminology includes condensed hydrocarbons, oil mist, oil aerosol, oil vapor, total gaseous hydrocarbons, total volatile hydrocarbons, total halogenated hydrocarbons, and the list goes on and on. ISO 8573 defines oil as a mixture of hydrocarbons composed of 6 or more carbon atoms. The lighter hydrocarbons with carbon atoms from 1 to 5, commonly called gaseous hydrocarbons or total volatile hydrocarbons, are the ones typically reported for breathing air analyses, and those are not included in this total oil purity limit from ISO 8573. Most of our clients in food and pharma are always wanting the lowest amount of oil possible. So that means class 1 or class 2, which requires analysis of not only oil aerosol, oil vapor, and organic solvents, which widens the cast of usual suspects to include off-gassing of the more volatile compounds associated with oil, such as organic solvents used to clean piping, threads and glue used to cement connections. Organic solvents, when detected, are reported by the laboratory but are not considered for the pass-fail criteria. One of the side benefits of using ISO 8573 total oil analysis methods is the ability to detect certain compounds that may produce off flavors in food products. One of the compounds we frequently see in our analyses are terpenes, such as limonene and pinene, which are great for scenting cleaning products. You know the ones I'm talking about. You can really smell them when you walk into the room. But perhaps that is not quite so desirable in your final food product. For classes 3, 4, and X, vapors are not required, as there would be no significant impact at the measurement levels greater than or equal to 1 milligram per cubic meter. Liquid oil, I'll only mention in passing because it's typically only measured when wall flow is present or heavy contamination is expected. And by that, I mean you can see it dripping out of a nozzle or at the point of use. There's a completely different method for analysis prescribed by ISO 8573. And when we get that type of call, the client's looking for someone to devise a decontamination plan. So liquid oil is not applicable to a compressed air monitoring plan. Oil lubricated compressors, by the nature of their operation, introduce liquid oil, oil aerosols, and oil vapor from the compression process. A well-maintained oil lubricated compressor in the food industry will have been designed to remove oils to very low levels. Now, if you have an oil-free compressor, it reduces the risk of oil contamination, but does not eliminate it because, if you'll recall, oil vapors can be drawn in through the compressor intake. The oil vapor then cools and condenses in the compressed air system and can be applied to your product. So while the risk is reduced by using an oil-free compressor, it does not mean that you shouldn't test for oil. Oil and organic solvents, as well as particles, can be introduced through the installation of piping when inappropriate bonding materials are used, improper piping, or from residues of cleaning agents. New installation of piping should always be purged extensively and tested before connecting to existing distribution piping. Distribution piping should be clean, oil-free, with low to no particle shedding properties. And when you combine moist air, food-grade oil, and a warm, oxygen-rich environment inside the air receivers, distribution piping, and even fittings, you can create an environment ideal for microbial growth. By installing a desiccant dryer, you remove one of those factors for microbial growth. However, I'd like to point out that although a desiccant dryer at, say, minus 40 degrees C can inhibit the growth of microorganisms, the dry air does not kill the microbes. Once the microbes are introduced back into a warmer and wetter environment, if they're present, they will begin to grow again. That's why point-of-use filters are either required or recommended for critical control points in the food industry. So now we've got a poll that we'd like to do. Does your country regulate compressed air quality in the food industry? So mark either yes or no, and if yes, please indicate your country in the chat box.
Okay, yeah, I've already set that poll live in the sidebar. Just to reiterate, does your country regulate compressed air quality in the food industry? And yes or no. And if yes, and only if yes, please type your country in the chat box. Right, Right. So we're looking at the moment, Ruby, about 60-40 in favour. Yes. So have we got any countries?
I see Canada and USA.
Yeah. Is that lots of Canada and USA? And some questions
I
flying
saw
by as
Brazil.
well. Brazil, USA. Is that correct? That is compressed air quality regulated in the USA and Canada as such? India, we've got India.
Oh, good. Yeah, I knew they did. So that's great. We've got someone on there.
Mexico. But the vast majority of those that answered yes are saying USA or Canada.
Right.
And it's settled out at 63% yes, 37% no. Okay, so shall we move on?
Yes.
Okay.
Okay, so now that we've identified the hazards associated with compressed air, let's move on to discussing air quality standards that you can use for compressed air monitoring. Currently, there are very few published air quality standards for manufacturers. The regulating and certifying bodies require monitoring, establishing limits, and ensuring that the air does not add contamination to the final product, but they don't tell you what that quality must be. On one hand, it's quite understandable because there is no one-size-fits-all answer. On the other hand, it leaves some wondering how to establish limits. As an analytical laboratory, we selected ISO 8573 as the basis for our compressed air testing program because it provides a common language for the compressor and filter manufacturers, the analytical laboratory, and the food manufacturer to use. Plus, it's an international standard used around the world. So for our global customers, it's an effective standard that can be applied across all their facilities. Whether you know it or not, you are probably using filters that are rated according to ISO 8573 classes. So it makes sense that you test what you're filtering to remove. This summary chart from ISO 8573 shows the contaminants, particles, water, and oil across the top of the chart. And then on the left-hand side, we have the purity classes. Class 0 is, let me point out that the limits at the top of the chart, like for class 0, 1, 2, are more stringent than the ones at the bottom. Class 0 and X, you'll notice, are at the top and bottom of the columns, and they have special circumstances. Class 0 is really a custom requirement by a user, and it must be better than Class 1 requirements. We frequently see a request for Class 0 oil. When that is requested, they have to give us what the limit is that is better than Class 1. You'll have to excuse me. I had some surgery on my throat about a month ago, so it gets dry a little bit. Class X limits are really kind of unacceptable for critical application like food. And if you notice, for particles, the limit is no longer described by quantity and size of particles, but instead by weight. These numbers right here. ISO 8573 states that particle classes 6 and 7 are for industrial tools and pneumatic fluid power operated machines, which traditionally use general purpose filters with a particle size rating of 5 microns for class 6 and 40 microns for class 7. And since the limits established are by weight, it's a different method for analysis than for the more stringent classes. These classes require that we determine how many particles there are in different size ranges. And as you can see, for water, it's a range of the more wetter numbers here, which would be for a refrigerated dryer. And then for desiccant dryers, you'd be looking at a class 1, 2, or 3. And let's see, for there are some, there's liquid water listed here. Excuse me. But liquid water is not applicable for critical applications. And for oil, X represents greater than 5 milligrams per cubic meter. Earlier, I briefly mentioned that I mentioned liquid oil. It would fall into class X, where heavy contamination levels are suspected, and a different method of analysis is required for liquid oil. As you can see, there are no limits anywhere on this chart for microorganisms or gases. ISO 8573 has not established limits for those contaminants, though they do have methods for analyzing them. You can select different classes depending on the contaminant. In other words, you don't have to pick a single class for all contaminants. You don't have to say, okay, I'm going to do class 2 for particles, class 2 for water, and a class 2 for oil. You don't have to do that. You can say, I need class 2 for particles, but I have a desiccant dryer, I have a refrigerated dryer, so I'm going to go with a class 4 for water. And then you can say, I need as low oil as possible, and select class 1 for oil. Speaking of what a great language ISO 8573 is, here's how to properly designate ISO 8573 purity classes so you can communicate to others what it is you need. The designation of ISO 8573 purity classes includes the specification name, ISO 8573-1, and the edition date. There's a colon and then the version. And then the purity classes are in numbers in brackets. So I've used the letters PWO so that you know that's the order they should always be written. So it's always particles, water, oil. We've got some examples at the bottom. What? I'm sorry. I got distracted. I apologize. There are some examples for direct contact with a class 221, indirect contact 242. And if you're going to eliminate one of the contaminants and not test for it, you just put a dash. We have a more detailed document that discusses further designations, but for now we're going to move on. ISO 8573 has a sufficient range of purity limits that allows manufacturers the flexibility to use for products from infant formula to potato chips. The purity classes are aligned with what is commercially available from filter manufacturers to remove these major contaminants. Performing a simple search on the internet for air compressor filters, ISO 8573-1 2010 provides pages and pages of compressor and filter manufacturer advertisements citing these purity classes to describe the quality of air that they can produce with their products. Many of them even have suggestions as to which purity classes should be used for various industries. There's a guide published by the British Compressed Air Society with input from the British Retail Consortium that recommends purity classes for the food and beverage industry. If compressed air comes into direct contact with your product, they recommend purity classes 221. That would be this here. And if it's indirect contact, like clearing a conveyor belt, then they recommend the use of classes 242. And as we just learned, that designation means class 2 for particles, class 4 for water, and class 2 for oil. According to the guidelines, compressed air quality shall be tested and verified at least twice per year or per the manufacturer's recommendations. Additional testing is also warranted whenever maintenance work or any activity that may affect the air quality is performed on the compressed air system. The guideline recognizes the importance of compressed air quality and states that compressed air should now be part of the prerequisite program, in addition to the hazard analysis and critical control points plan. Whenever maintenance is performed, a representative selection of the air outlets shall be tested to confirm that the compressed air meets the relevant purity classes. Okay, so for those of you struggling with determining what specs you should use, this is a solution from a reliable source that you can use. We're going to have a document to provide Simon after this presentation with various links to some of the things that I've been talking about. Oh, looks like we have another poll. So, do you currently test your compressed air quality? We've got a couple of yeses here. Yes, if you're using ISO 8573 standards. Yes, if you're using non-ISO 8573 standards. Or no, you're not testing compressed air.
Yep, I invite you to vote in the poll. Question, do you currently test your compressed air quality? Yes, against ISO 8573. Yes, against non-ISO 8573, or no, not at all. Okay, and it's looking like around 60% do not test the compressed air at all, and then around 20% split. 20% do use ISO 8573 and 20% do not. Okay, is that sort of what you
That's interesting information. Yeah, good information to know.
Okay, move on then, please.
Okay, so now let's discuss how to assess the risk of your system. Generally, the steps needed to assess the risk of product contamination are as follows. Identify potential hazards, assess the risk of harm, assess existing control measures for adequacy, assess if extra controls are needed, schedule regular reviews to see if the controls are working. So we discussed what the potential contaminants or hazards were earlier in the presentation: particles, water, oil, and microorganisms. We also discussed different standards by which you can measure these contaminants. Armed with this knowledge, we can begin to assess the risk of product harm. The following checklist can be used to assess the health of your system. The blank checklist helps you document information about your compressor, install filtration, point of use, and sampling port connections. Once you have this information, you assign the level of risk for each element with a numerical value, with 0 being no risk and 5 being certain risk. When you're trying to determine level of risk for each row, this list might help. It's going to show you the typical materials for parts of a compressed air system in order from best on the left to worst on the far right. And there seems to be a general agreement that stainless steel, along with certain specially manufactured polymers, can form a good backbone for the distribution of compressed air. So, if you look at the list, The worst type of piping that you have would be black iron or galvanized piping. The very best would be a stainless steel. Um, and then you just kind of estimate where the others might fall into. This is just general information for you to use. We recommend using stainless steel fittings when connecting air sampling equipment to the sampling outlet. And if flexible tubing must be used, we advise against using rubber tubing or any tubing of unknown material. We have some recommendations that I can provide you later for low particle shedding tubing. The material list shows information that's fairly common, although many of the entries made relating to piping, seals, sealants, and valves are usually not discovered prior to your initial sampling. While there is a final score on this filled out form that adds all the columns, adds all the column numbers, what you really want to do is look at those areas where you have a medium to high risk. So in this scenario, the problem areas are the compressor piping and distribution piping. And that's because we've got cast iron as the type of piping. The yellow tubing that's being used before and after the point of use is suspect, and the lack of point of use filters. Because there are various types of piping throughout after the main filtration and a refrigerated dryer with no point of use filters, there is a high risk for contamination from rusty particles and microorganisms. So use that list to assess your system, and then that will be part of your process in figuring out what your limits should be and what your risks are. After assessing a risk across your entire system, you have to synthesize this information with the needs of your particular products. Determining specific limits is key to the rest of this process. Without setting specific limits based on the risk of product harm, you cannot adequately assess existing controls, assess if extra controls are needed, or determine an appropriate monitoring plan. SQF, FSMA, and FDA state that you need to set limits. But in our experience, we are finding that customers don't have enough information to do that. So they frequently default to setting limits, but instead of doing so they frequently default to not setting limits, but instead doing a diagnostic test where we tell them how their system is currently performing. Then, armed with that information and sufficient data points, information from that risk assessment, which will tell them what kind of filters they have, they're better able to determine what limits are most practical for their facility. Setting your limits may be the most difficult part of the process. Although we reviewed specifications like BCAS's direct and indirect recommendations early in the presentation, setting your limits requires you to take your compressed air system information and apply it to your specific product. I do caution you to not go overboard and decide that you want the best and set your limits to a class 111. If your product doesn't need it at that level of purity, you could be setting yourself up for unnecessary headaches. Because remember, if you have a limit and then fail to meet them, you must investigate the cause of the failure and take corrective actions and make corrections and document everything to satisfy your certification requirements. So it's best to assess your risks and set appropriate limits. I thought you might be interested in seeing which classes other food manufacturers use. So here's some examples. Oh, the examples have been there for a while, sorry, of what other manufacturers have selected. You've had a chance to look at them. There's this particular manufacturer decided that baby food was a high risk for particles. So they set it at a class 1, but not so much for water. It's a class 3, and oil was class 2. As you can see, they vary from a variety of different purity classes. I could list more, but I'm just showing you the short list just to give you an idea of what other manufacturers do. We've put together a chart and grouped the various purity classes for each contaminant by risk. You can use this guideline once you have assessed the risk of your specific product. So the red is for high risk. So you would want the most stringent purity classes, which would be the class 1, 2, class 1 to 3, which would require a desiccant dryer, and class 1 or 2 for oil. We've then said that the other classes 3 to 5 for particles, 4 to 6 for water, 3 to 4 for oil, are a medium to low risk. And then the very bottom, the gray section, is where you're not using it on your either directly or indirectly. More than likely, this is for tools, certain pieces of equipment, but certainly not appropriate for compressed air used on your products. Excuse me. Now that excuse me. Now that you've assessed your risk and established limits, you're ready to begin testing to see if your current controls are performing to the standards you've just determined. What do you need to establish a monitoring program? But first, you have to answer a few questions, like, where do I test? Results from air samples should be representative of the air used on your products. Try to capture samples as close to the point of use filtration. Identify any critical control points. Take sufficient samples that cover all the variations in your air system. In other words, old piping versus newly installed piping, furthest distance from the compressor, facility variations, outlets where piping goes outside of the building and then re-enters the building, filtered point of use versus non-filtered. So how many samples should I take? There are different answers depending on, where do I test? No. How many samples should you take? There are different answers depending on what you're trying to accomplish. We know that current SQF and other certification requirements will accept 1 sample annually. From our experience, FDA auditors expect to see more data from throughout the facility that includes all product lines. To determine if compressed air quality is in a state of control throughout the year, 1 sample is not enough. The following are some sampling plans that you can use and combine to determine what is best for your company. Sampling strategies should be robust to ensure that the air provided to all points of use is of consistent quality. There are several sampling options to consider when assessing your system and its control. Pick a percentage. Pick a percentage of your outlets, say 25%, 33%, 50%, to sample annually. We recommend sampling throughout the year to include seasonal changes, production variations, and maintenance schedules. For example, you have, let's say, 24 outlets with direct contact. You could decide to sample 33% annually. So sample 2 outlets every quarter for a total of 8 samples for the year. Pick 8 different outlets the following year, and after the 3rd year, you would have sampled all of your outlets. And in the process would have gathered valuable information that you can then use to make an educated decision on the true monitoring plan that works best for your operation. Another plan would be based on maintenance. Take samples before and immediately after compressor filter changes and point of use filter changes. Also, sample after any major changes of the compressor or distribution piping. Data obtained after 3 to 4 filter changes can be used to establish a trend analysis determining that air quality is in a state of control or not. Filters are being changed at appropriate intervals or not. And major changes did not negatively affect the air quality. This strategy can also be combined with the percentage-based sampling plan. A minimal-based plan would take 3 or 4 samples, say one as close to the compressor filtration as possible, one at the furthest point from the compressor filtration, like at the end of a line, and then 1 or 2 somewhere in between. You can review results to see if there's any degradation of air quality the further you get from the main filtration. This will also take into consideration possible piping contamination. And then there's the single, lonely, one sample. Take one sample from a critical control point. Select a different point of use each time you sample. Taking one sample is a good first step and will satisfy some requirements for GFSI required certification audits. While some may call this a monitoring plan, I don't think it is. And the last question is, how often do you need to test? Your options are annually, semi-annually, quarterly. While taking samples once a year is convenient, we think taking samples at various times of the year is a better gauge to assure consistent air quality. BCAS's Food and Beverage Best Practices Guideline recommends semi-annual testing and anytime major work is performed on the compressed air system. Quarterly is a trend analysis can provide useful information on the state of compressed air quality at various times throughout the year. By noting filter changes, compressor maintenance, both routine and emergency, and sampling dates, you can track the quality of your compressed air by outlet or by product line. This frequency can then be reduced once you have sufficient data supporting consistent air quality. Reviewing the results of your air test will provide the information you need to assess if your controls are adequate. If samples fail to meet your established limits, you will need to either reassess if the limits were set inappropriately or add additional controls, such as point-of-use filters. If controls are inadequate to achieve the desired air purity rating, additional controls obviously are called for. For instance, you add controls where none are in place, like adding a refrigerant dryer where there is none, or to add controls to existing controls, like adding a desiccant dryer to a refrigerant dryer. And for the final step, scheduling, excuse me, and for the final step, this pertains to periodic reviews, like semi-annual that BCAS guideline recommends. Excuse me. But whatever you do, don't wait until right before the audit. We've received panicked customers calling who are finally reviewing the results right before the audit and finding that they should have taken some actions based on the test results. That's not a good situation. Thoroughly review and understand your reports. Call your lab, ask them to explain it, and review your historical data. The last thing you want to do is be scrambling around at the last minute right before an audit. Compressed air systems are not static, but dynamic, always changing. Component parts break down and malfunction, requiring maintenance or replacement. And there's not always an obvious indication that a device which is plugged in and running is not performing to standard. Regular testing hedges against the possibility of underperformance or non-performance. Compressed air quality is a critical aspect of sanitation in the food industry. While regulation is still in its infant stages in some places, the core desire to protect consumers is enough to warrant regular air testing, as well as to ensure that equipment and processing environments are operating efficiently. Testing, while it does cost, stands to safeguard against the possibility of greater cost of damage or incident. That brings me to the end of this presentation. I invite you to stay for the questions and answer section and download the supporting documents that we've made available. I'd also like to welcome you to call me or email me with any questions you may have about compressed air testing in the future.
There's been tons of questions, absolutely tons, but thankfully, Tori from Trace Analytics and lots of the other members who obviously are well into testing their compressed air and understand it, have answered very well. I know with probably 7 minutes to go, we're not going to pick up all the questions at all, but what we will do, we'll collate them all. All this chat is captured, so we'll collate all of that and we'll trim it down to the questions, pick through it, and we can send out a follow-up email with answers to some of those if we don't get to them.
Absolutely. I apologize. I'm a little long-winded.
No, it's fine. Right, so let's, have we got any question? Jennifer, how do you test for water and oil? How do you test for water and oil?
Okay, so using ISO 8573 methods, there's different acceptable methods. Certainly hygrometers can be used to measure water. In the service that we provide, which has to be worldwide so that we can send equipment everywhere, we use detector tubes for water. As far as oil goes, there are two different types of collection that we do for class 1 and 2. One is a charcoal tube that collects the vapors, and then there's a filter that collects oil aerosols. That is a slight variation to what ISO 8573 recommends. They recommend doing an infrared analysis. We do a gravimetric analysis for oil aerosols. Once we have those two test results, we combine them and give you the result for total oil for class 1 or 2. The other classes only require the oil aerosol. Okay,
thanks, Ruby. Tom's asking about how much does it cost. Can you give us an idea? If you contact Ruby, the details are on your slides, aren't they? So you can contact Ruby directly about cost.
Absolutely.
It will vary on the types of costs and the types of testing, etc., I imagine.
Yes, but if you were wanting, I can give you some general pricing. Typically for a sample that's going to be of the more high risk classes, it's going to be about total about $300. If it's going to be something in the mid ranges, what is that price? I think it's closer to 200, 225. Now I might be stretching the truth here. So we can certainly send you a price list that has it all broken out.
But sort of maximum high risk, it would be about 300, did you say? Yeah. Okay, Stephen's asking, do I legally have to test in the UK?
Legally, I don't know that there is a law.
Well, I can say from the UK, being based in the UK, that legally you're obliged to provide safe and wholesome food, and anything that renders it injurious is illegal. So compressed air and the safety of that compressed air, if it's used in a food environment, is potentially a hazard that could render it injurious. So indirectly, yes, there are legal requirements, but probably not specifically. Yes, so I think that's probably the case.
And I was just handed my price list, so I was right. It is $225 for the mid-range.
Right, brilliant. Okay. Are you offering any introductory slight discount for the IFSQN members? Oh,
Yes, I believe that we have a special of $50 off analysis.
yeah. Well, I'll forward that in the email as well. Okay, let's have a look. Any questions about testing? Can you claim test compliance if you don't follow what the standard states? Stephen, can you claim test compliance if you do not follow what the standard states?
Well, so as far as I know, unless if your country has adopted a particular standard, the manufacturer is the one that is responsible for saying, this is what I am going to do. We have some customers that have custom specs. Certainly in the pharmaceutical world, that is very common, where they kind of pick and choose what they want and create one that's just for their corporation.
Okay.
So it basically just depends on how well you've got everything documented so that when you're audited, you can show all the documentation.
Okay, makes sense. Louis, are the testing methods verified and certified? Do you provide lab certificate with the results?
Yes, as an accredited laboratory, all of our methods are reviewed for our accreditation.
Okay. Stella is asking, you might not like this one. If I want to test the air by myself, should I buy a testing kit and send it to the lab? Oh, how do I collect the sample?
Oh, okay. So absolutely, we provide rental of the equipment. We provide sales of the equipment so that you can take your samples and send them into the lab for analysis.
Oh, right. Okay.
That's how our program works.
All right. I see. Jeremy is asking about nitrogen. I don't know if you can see that one.
You know, I cut that section out because I was so long-winded. But as you know, SQF is coming out with their Edition 8 is going to become effective in January. And it is requiring any inert gases that are used directly on your product need to be tested as well. So for some of the common gases like nitrogen and oxygen, absolutely we can give you gas purity testing. Some of our clients also like to make sure that the distribution piping is correct. So they'll use this particle water and oil testing that we provide to check the piping of their nitrogen systems.
Okay, great. And Sarah's also asking about, we use food grade nitrogen to blow plastic pouches that are filled with juice. What type of filter is required before the use point?
I'm not aware of any filters that are required, but I haven't checked SQF's updated, or even if they've got any updates to their guidelines for this new edition. Usually it lags a little bit before that comes out.
Perhaps we can have a look at that, and that could be one that we may be able to follow up on later.
Absolutely, we can do some research on that for you.
Okay, Kelly, what are the typical air quality standards for air used for analytical instruments?
So those are probably going to be a little bit different. And quite frankly, we focus on air that is either used for breathing or air that is being used for consumer products. As far as air used in the laboratory, I'm sure there are some, but I don't have them at the top of my head.
It's a bit left field, that one, I think, isn't it, really? Will you be able to share the information on the nitrogen generating system?
Yes, I certainly can.
Okay.
It was really just a couple of sentences, because that was not the thrust of this presentation.
Yeah.
That's probably a good topic for another presentation, though, Simon.
Yeah, why not? If there's enough interest, yeah, just type in the sidebar if you want to see nitrogen. Elizabeth, are there any recommended limits out there for microorganisms?
I'm sorry, say that again.
Are there recommended limits out there for microorganisms?
For compressed air, not that I have found yet.
No.
What a lot of our customers do is use their environmental or their product limits and judge their compressed air by that.
Yes, that makes sense. Yes. I think we're probably getting to the end of it. Oh yeah, a couple of nitrogens there coming in. Joseph, we use air jet coding in our plant. Does this air need testing for GFSI?
They use what?
Air jet coding. Air jet coding.
I have no idea what that is.
No. I think it's the coding, date coding of. I would say if it is date coding of packages and it's inkjet and they use compressed air to drive the ink, I would say the chances of direct or indirect contact with products are probably low. But it probably runs off the same compressed air system that the rest of your factory does. Let's have a look. There are a few for nitrogen. I think what we'll do is that there are lots of questions further down. If we scroll far enough, there are dozens of questions. So I think we'll collate them all and follow up afterwards, because we have gone past the hour and I know a lot of people are busy and need to get back to work.
Sure.
So I'd like to say, Ruby, thank you to Trace Analytics and to yourself personally for this fantastic presentation. Stimulated a lot of debate and answered a lot of questions. So thank you. And I know, obviously, you've had an operation, a procedure, and it was a struggle at points, but you did fantastic. So thank you very much.
Well, thank you. We appreciate the opportunity.
Yeah, and I hope to see you again soon, and we'll be in touch by email. We'll send all the documents, the links to everything, and we'll give everything to the attendees, won't we?
Great. Yeah. Thank you so much.
Okay. Right, ladies and gents, the last thing to do is to issue with the certificate of attendance for today, which I've loaded in the sidebar now. You click on that download now button. And then when you go to the sponsors page, you will actually see on there, there's a Trace Analytics $50 discount on that page. So do have a look at that and grab that. But you can also then click the link to download your certificate from Dropbox. Please remember, you have to add your own name to the certificate. I'm not adding 1,300 names to certificates. I just don't have the time. So you can either print it and sign it, or open it in an image editing package and type your name, and that's that. And I know still, even after saying that, dozens of you will ask for your name on the certificate, but I can't do it, I'm sorry. Thanks for your attendance today. Thanks again to Trace Analytics, our kind sponsor, and for doing this presentation today, and to Ruby Ochoa, the president. It's a great presentation. We will follow up with an email with the video, the slide deck, and all the documents we've talked about, the checklist, etc. And then we'll probably do another follow-up email once we've got the answers to all of the questions, because that might take a little bit of time. So I'll see you next week for David Rosenblatt. And just a reminder, that is Food Safety and Employee Safety, a behavioural approach to creating synergy by integrating two agendas. Basically, most of things that do go wrong in food safety and occupational person safety relate to people and their behaviour, whether it's a technical issue or it's actually a pure human behaviour issue. So look forward to seeing you next week. But for now, happy Friday. Enjoy the rest of your day. Have a great weekend, and come back all refreshed and ready to fight the fight next week. Okay, take care, everyone. Bye.